Hello, and welcome to Section 3.9, Related Rates. Related rates problems are application problems that use the chain rule or implicit differentiation to describe how one thing is changing relative to another thing, and that other thing is changing relative to time. So the hard part about related rates problems is coming up with the formula or relationship between some of these related items. But there is a procedure that can help guide you. But you're going to need to review possibly some things from trig or from geometry, because you never know what kind of problem you might get. For example, you might need to remember how similar triangles work, or let's say the volume of a sphere or surface area of a sphere, things like that that you may not just have handy every day. So these are the steps to solving the related rates problems, and I'm not going to talk too much about them right at this second because I don't think it does much good unless you actually have a problem to look at. But with any application problem, always draw a picture if you can. Even if it doesn't seem like if it's one thing, like, a ball, or, it might be a man walking. How do you draw a man walking? Well, do your best to try to draw a scenario that shows how the things relate to each other. So let's look at an example. The surface area of a sphere is changing. And we're given that the radius of a spherical ball is increasing is 2 centimeters per minute. And we're asked at what rate is the surface area of the ball itself increasing when the radius is 8 centimeters. So we're being given a situation where we have a ball whose radius is changing, and we know the rate at which that radius is changing, and we're supposed to find the rate at which the surface area is changing. So you can see there's that dependency, that chain of dependencies. The surface area of the ball is dependent on the radius, and the radius of the ball is dependent upon time. The radius depends what time it is as to how many minutes have elapsed, because it's increasing by 2 centimeters per minute. So step one, draw a picture of the situation. So I'm not really, on a piece of paper, I'm not going to draw, I can't draw a three-dimensional object, a ball, but, this is kind of a cross-section, and you're just kind of thinking in terms of, okay, as the radius changes, the surface area is going to change, and the radius is moving outward, and after 1 minute, it increases by 2 centimeters. So if I use Desmos to continually increase the radius of this circle, you can kind of see how it's increasing and how the radius is going to affect the area of the circle, and if we were considering this in 3 dimensions, the surface area of a ball. So we've drawn our picture. Now what we want to do is find a formula or equation to relate surface area and radius. So the surface area formula for a sphere is 4 pi r squared. And notice that the sphere's surface area depends on the radius. So since we want the instantaneous rate of change of the surface area of the sphere, we want to differentiate this. So using the chain rule, we're going to be differentiating this. And we're using the chain rule because, remember, that radius is actually a function of time. And we want to find the derivative of s with respect to t. Now, there's no t showing up in this formula, but we know that kind of hidden within this radius is a function of t. So we're going to be using that same type of thinking we did with implicit differentiation. So the next step is, once you have your relationship, you want to differentiate. If you have an implicit or an explicit equation, it depends on how you differentiate. But in all cases, you're going to be using the chain rule at some point, whether it's, as just par for course for doing implicit differentiation, or if you have some other function, you just want to use the chain rule. Time is always your independent variable for the most part. So back to our problem here. So I'm going to find the derivative of the surface area with respect to t, and using the chain rule, I'm going to differentiate this as 8 pi r, that's the derivative of the outside, times dr dt, that's the derivative of the inside. So what do we do with this? Well, we were given that the radius is changing at a rate of 2 centimeters per minute. So, right, so that's dr dt. So I'm going to have to fill out dr dt and r in this equation in order to get my instantaneous rate of change of the surface area. So that leads us to step 4. State which variables and rates are known. And so like I said before, dr dt is 2 centimeters per minute. We were given that's how the rate's changing. And we were asked to find the rate at which the surface area is increasing when the radius is 8. So we're given that this r is 8. So we're going to, in step 5, plug in those values into our new relation that we've found the derivative of. And when I plug in dr dt is 2 and r is 8, I get 1.8 pi centimeters squared per minute.